Now, if we have some volume changes that take place, if the left ventricle fails, and this causes, because, if the blood backs up into the lungs, this can cause pulmonary edema. It can lead to shortness of breath or feeling like you're suffocating. And usually, depending on the severity of it, might have to be drawn off. But usually you have to look for the deeper issue of what could have caused the backing up of the blood into the lungs. If the right ventricle fails, the blood could actually back up into the vena cava. And this could create, either edema in a particular system of the body, or it could create edema throughout the rest of the body, because that vena cava is bringing blood back to the heart from all areas. A system that can be affected is the liver. And we could also see that the fluid could build up in the abdominal cavity. I've mentioned the ascites before. We can, it can lead to this distension of the jugular veins. We can get the swelling throughout different areas of the body. The overall problem, if one of these occurs, if we have the blood backing up in the left or the right, it can eventually lead to heart failure. So when someone is suffering from an edema problem, if it's something that becomes chronic, it's a really good idea to look at the heart and the beating of the heart and so forth to try to determine where that edema might be coming from. So this is showing you what can happen if the blood backs up and we get the pulmonary edema. This one is showing what can happen with the systemic. So if we begin to have that backup into that vena cava, it can move into other organs of the body. It can move into other tissues, legs, feet, that sort of thing. So edema is, or a chronic edema, acute edema also, but a chronic edema definitely is going to be indicative of something going wrong, and the heart should be a place that should be looked at. Now, with our heart and the volume and the blood, one of the things that we can look at for function of the heart to see how well the heart might be performing, we can actually look at something called cardiac output. Basically, the amount of fluid that is ejected by those ventricles in a 1 minute time frame. Cardiac output is some math. Basically, heart rate times the stroke volume. Cardiac output on the norm should be roughly 4 to 6 liters per minute while at rest. That's why I said when we were talking about the chapter on blood, a red blood cell makes its travels around the body in about a 1 minute time frame. Now, there are different factors that can affect the cardiac output, this amount that's being pumped out. When we exercise will increase the cardiac output. And in some cases, like it shows right there for the world-class athletes, when they're doing their training and their whatever they might be a world-class athlete in, look at how much they can actually increase the volume to. They can increase it to 35 liters per minute. And the heart will match this. The body will match this because you can train for it to do that. Now, we do have something called cardiac reserve. Basically the difference between the person's maximum output and they're resting. So if you had a person that's normal heart cardiac output, let's say it's 6 liters per minute, but during their time that they're exercising, it's 35 liters per minute. 35 minus 6 is going to be cardiac reserve of 29. The way that we increase our cardiac reserve is we do this by, fitness. You hear people talk about, oh, well, the heart is a muscle. Yes, it is. Needs to be exercised just like any other muscle in the body. The effectiveness of this cardiac output is definitely affected with inactivity, obesity, disease, age. It does get affected by many factors. Our heart rate, this is our pulse. It's that surge of the pressure, and usually there are different areas throughout the body. There's like 9 areas that you can palpate for the pulse, and it lets you basically determine how many beats per minute. And so infants have a normal heart rate of about 120 beats per minute. Young females, about 72 to 80. Adult males, 64 to 72. Now, as we get older and definitely into the elderly, that heart rate might rise because it's actually working hard to get the blood through the vessels, because other things happen to the vessels of the body. And it could actually be some stuff happening with the heart also. So the heart rate might go up in the elderly. Some of the things that are associated with heart rate, tachycardia means that the heart rate is too fast. Bradycardia means it's too low. And when we have different things that can begin to affect the heart rate, these are going to be chronotropic agents. Basically, these are factors that can either raise or lower the heart rate. There can be positive factors, and then there can be negative. The positive will raise it, the negative will lower it, okay? And then at different times, even throughout the day, the heart rate will vary, okay? Like, for example, they mention during sleep. Yes, during sleep, the heart rate goes down. The chronotropic effects, those positive and negative, this is where the autonomic nervous system. Now, remember, the heart does not depend on the nervous system, but the nervous system can affect it. So that autonomic nervous system will affect or modulate the rhythm and the force of the beating of the heart. We're going to find in our medulla oblongata and the reticular formation the cardiac centers. That is a center of the brain. We don't have to do anything about it, okay? It is monitoring that heartbeat 24/7. And some of the neurons can stimulate the heart, and that's going to be the sympathetic stimulation. Others are going to inhibit those signals, and that's going to be the parasympathetic. So even though we don't depend, okay, they can affect it. With the sympathetic system, one of the things that happen, they release the norepinephrine, which is a precursor to the epinephrine, if you guys remember us talking about that. So what will happen is they will activate a second messenger system in the cardiocytes and in the nodes, and that begins to affect those plasma membranes and the channels. And since it's the sympathetic system, that accelerates depolarization. So that means it wants to speed up the heart rate. In some cases, it can take it as high as, it can take it over 200 beats per minute. Now, this becomes a problem. If the heart is beating that quickly, basically it cannot fill back up with blood completely. And that in turn affects our stroke volume and the cardiac output. This effect, if it begins to occur and last for a significant amount of time, it can possibly lead to a heart attack or the heart just failing. For the parasympathetic, this one, the overall goal, okay, slow the heart down. So it will use acetylcholine and, basically it will take or affect the cells, and this time cells get hyperpolarized, meaning they go below the resting membrane potential and they can't be stimulated. So if they drop lower than that resting membrane potential, they have to, basically the heart can't get stimulated and we can slow it down. Now, due to the vagus nerve, the two systems, working together, and then the heart itself, because, the heart's doing its own thing. We have what's called vagal tone, and that's the reason that we can keep that heartbeat to roughly the 70 to 80 beats per minute. When we look at those cardiac centers, even though we have that primitive portion of the brain that's monitoring the heart rate, there are higher brain centers that can affect the heart rate. For example, emotions. Emotions can definitely affect the heart rate. It can make the heart rate go up. It can make the heart rate go down. And these are going to be higher order brain activities. We also find that the medulla, we have those proprioceptors that are located throughout the joints and the muscles and so forth in the body. And those can actually affect the heart rate. Maybe if, stand up too quick, get up from lying down too quickly, it can actually begin to affect the heart rate, because the heart rate's going to have to compensate for the areas of the body that had not had to be receiving blood, but now do, and you got to give it just a few seconds to catch up. So the heart will have the ability, or these proprioceptors, the motion, the movement will affect the heartbeat. When we look at the baroreceptors, these are the ones that are monitoring pressure. They're found in the aorta and the internal carotid arteries. So if they begin to detect anything about blood pressure, their job send the signals to the cardiac center of the brain so that we can either increase or decrease the heart rate. And if we have increase in heart rate, it's because blood pressure has dropped. And if blood pressure increases, it wants to decrease the heart rate, because the overall goal, keep that blood pressure within the normal limits. It's not a long-term solution to blood pressure problems, but it does help affect the blood pressure problems. The chemoreceptors are going to pick up information about the chemicals, the pH, the CO2, and the O2. So this is going to be involved with the respiratory control center, and their job basically increase or decrease the blood pressure, or so that we can match the gases. Make sure that the fluid doesn't get too acidic or too basic. Make sure that we're keeping O2 at good levels, making sure we're getting rid of CO2. So the chemoreceptors will help with that. Their job is done based on negative feedback. And the goal is to make sure that we maintain the overall homeostasis of the body.